Okay, we'll start the class now. So today we'll start a new topic, which is design of cotter joints. So far we discussed about different types of joints. In that we have discussed about two permanent types of joints. There are riveted joints and welded joints, which comes under permanent joints. Now we are going to discuss about another temporary type of joint. So bolted joints, we already discussed about bolted joints. They are temporary joints. Even these cotter joints are also comes under category of this temporary joint. Temporary joint in the sense you can, if you want, you can assemble or you can dismantle the joint without breaking the joint components. Then we call that kind of joint as a temporary joint. So we know in case of a bolted joint, you can dismantle or you can disassemble the connecting parts just by removing the connection between removing that bolted connection. Here also the same thing, you can assemble or you can disassemble without breaking the joint. So before going to discuss about this cotter joints or design of this cotter joints, first we should know what is cotter. Then we'll see what are different types of cotter joints, and then we'll see what is the design procedure for those cotter joints also. So here at the beginning itself I am saying that so the design of cotter joints, so in examination point of view you will get a question. If you get a question, you will get a question for 15 marks. So only thing what you have to do is you need to use your data book to solve this problem. So in the data book, he has given all the formulas. So what are the design criteria formulas, or what are the design failures of a joint? So based on that, you can identify the joint dimensions also. Anyway, we'll see that we'll go for the design of a particular cotter joint. Okay. So first we'll see what is cotter, then where we can use this cotter joints, and then we'll go to the different types of joints, and then in that we'll take up a design of those joints one by one. So now if you look at this figure, this is what we'll call it as a cotter. This one we'll call it as a cotter. So if you look at this diagram or picture here, it is going to be a rectangular cross section. Always the cross section of the cotter is going to be rectangle here. You can see the cross section here. Here this is the cross section which is in the form of a rectangle, and he said that it is a flat wedge. Wedge means so something like a tapered thing is there, we'll call it as a wedge. So if something is tapered, we call it as edge, so that's why we are calling it as a wedge. So you can see the taper may be on either on one side or both sides. See here, taper in the sense whatever may be the dimension width at this location, it is not the same. The width is gradually decreasing from top to bottom, are increasing from bottom to top. So maybe sometimes there is a taper on both sides, sometimes only on one side. So this type of component, what we'll call it as a cotter. So why taper is providing here is to, like I said, so these cotter joints are the temporary joints. Whenever you want, you can assemble, you can disassemble. So that means, so this taper will provide that facility. So by providing the taper to the cotter, so it is easy to adjust. That is one reason. And another reason is you can easily insert and you can easily remove the cotter from the joint, so that you can disassemble the joint also. So that is the definition for a cotter. A cotter is a flat wedge shaped piece of rectangular cross section, and its width is tapered either on one side or both sides from one end to another for easy adjustment. Then the taper, we are talking about the taper. So the taper is varies from 1 in 48 to 1 in 24. So what is the meaning of this 1 in 24 or 1 in 48? So 1 in 48 means, so if I take a length of 48 mm, then the taper is going to be 1 mm. If I take the length of the cutter as 48, there should be 1 mm taper in the 48 mm length. That means here the difference between the width at bottom and the width at the top is going to be 1 mm. So that is what we'll call it as a tapper. Tapper is nothing but the width, the difference in the width of top to bottom. So that is nothing but 1 mm if you choose 1 in 45. If you choose 1 in 24, for every 24 mm length, so there is a, if you come down, there is a decrease in the width of the cotter by 1 mm, or if you move up, there is an increase of 1 mm in the width when you move from upward direction from the bottom of the cotter. So that is what we call it as tapper. It may be increased up to 1 in 8 also. So that means depending on if locking device is provided. So in case of locking devices, the tapper may go up to 1 in 8 mm also. So the locking device may be tapper pin or set screw used in the lower end of the cotter. So then the cotter, so the material, if you think about the material of this cotter, generally these cotters are made of either mild steel or wrought iron. Cotters are made of mild steel or wrought iron. Okay, so now, okay, so this we already discussed. A cotter joint is a temporary fastening and used to connect rigidly two coaxial rods or bars which are subjected to axial tensile or compressive force. So here, this is the application of this cotter joint. So when you are going to use cotter joint means whenever two rods or bars which are coaxial. Coaxial means, what is the meaning of coaxial? The axis of these two rods. So here it is used to connect two rods. I have one rod. This is one rod. Maybe this is another rod. So coaxial means whatever may be the axis of this rod and the axis of this rod. So for these two rods, this axis should be coaxial, means they are on the same line or they are coinciding. If I insert one into the other, the axis of this rod and this rod, this is rod 1 and this is rod 2. So if I insert this rod 2 into rod 1 or rod 1 to rod 2, the axis of these two should be coincide with each other. So then we'll call it as a coaxial rods. So are bars which are subjected to axial tensile or compressive force. That means, so this cotter joint can take only axial load. So that means that axial load may be either tensile load or compressive load. That means either I can apply the force in the positive tensile direction, something like this, it will be tensile load, or I can take the compressive load also. So only these cotter joints can take only axial load. So they cannot take any other load other than this axial load. They cannot take shear load or bending load or whatever you can call it as. So other than axial load, they cannot take any load. So they generally, these cotter joints are temporary joints which are used to connect two rods which are coaxial, and they are, if they are subjected to only an axial load. The axial load may be either tensile load or compressive load. So then this is based on this, if you look at the practical applications for these cotter joints, so one such kind of application is a piston rod is connected to cross head of a reciprocating steam engine. So there we can use this cotter joint. This is one of the application. Then joint between side spindle and fork of a valve mechanism. This is another application. Then joint between piston rod and the tail rod. This is another application for this cotter joints. Similarly, in case of foundation bolts also, in case of bolted joints, we might have discussed about these foundation bolts. So in there also you can use this cotter joint. So these are the four practical applications of this cotter joint. So of course, the first one, nowadays the steam engines are obsolete. Nobody is using the steam engine, but still when in that application these cotter joints are used. Okay, so these are the applications for these cotter joints. So now we'll move to the next one, that is what are different types of cotter joints. So like we said earlier, we have seen the definition for a cotter joint. So in case of a cotter joint, so the condition should be the joining two rods or bars. Whatever two rods which you are going to join through this cotter or cotter joint, they should be coaxial. and also they should be subjected to a axial load. So by satisfying these two conditions, we can arrange the joint in a different format. That means in one case I'll use only one cotter. If I use more than one cotter, something like that. Based on that, or some case I will use a for a cotter, along with the cotter I'll use a jib. So like that, based on that, the cotter joints are classified into different types. So they are, one is, like I said, I'll use only one cotter. So if I use only one cotter, I'll call it as a socket and spigot joint. If only one cotter is used, so that is called socket and spigot cotter joint. Then, okay, if you want to look at the picture, okay, it's not highlighting. Okay, no problem. So then you have a sleeve and cotter joint. Then you have jib and cotter joint. So like I said, you have these three types of cotter joints. One is socket and cotter joint. The other one is sleeve and cotter joint. The other last one is jib and cotter joint. I think all of you familiar with these three joints because you might have drawn these joints in our CMDP course. Anyway, what we'll do is I'll show you some video of the joint so that you will be familiar with these joints, and also while discussing about the design criteria, it is going to be somewhat more clear to you. So let me go to that files. Yes, so just go through this. This is the first one, what we'll call it as socket and spigot joint. So you can see the figure here, how it is. The joint is formed also. So from this diagram, you can clearly see that the joint consists of only three components. So this is what we'll call it as spigot, and this is the cotter, and this is socket, and this is spigot, and this is the cotter. So this rod we'll call it as a spigot, and the sleeve kind of thing what we'll call it as a socket, and this is the cotter joint. If you look at this picture here, so both spigot and socket have a rectangular hole in those two components. So now the socket is, or the spigot is inserted into the socket such that these two holes, the holes in these two components will coincide with each other. Once it is done, then this cotter is inserted into that. So this is the joint what we'll call it as socket and spigot joint. And similarly, I'll show you other joints also, which is the next one. Sleeve and cotter joint. So next type of joint is sleeve and cotter joint. You can see this here. Now here also you have only three components. One is, here we'll call it as a rod instead of spigot, or you can call it as spigot also. This is what we'll call it as a rod. Okay, I'll go to the next one. All right. So here this point, this component we'll call it as a sleeve, and you have a two rods, and you have a two cotters. So in each cotter there is a, again here some rectangular holes are there in this and this. Even in the sleeve also two rectangular holes are there. So now these two rods are inserted into the sleeve such that the rectangular hole in each rod and the sleeve will coincide with each other. Then these two components are locked or joined through these two cotters which are inserted into those two joints. those two components. So those two holes, if you insert this cutter into this hole and this hole, automatically they are locked, or you can say they are joined. So this is what we call it as a sleeve and cutter joint. So again here, the sleeve and cutter joint are also capable of taking only axial load. So then if you go to the next one, that is the third one, that is jib and cutter joint. You can see that also.
And cotter joint. This joint is used to connect rods of square or rectangular section. The end of one of the rods is made into a fork. The end of the other rod is simply square. Both the fork and the rod has slots for carrying the nib and cotter. The rod end is inserted into the fork end, and in proper position, the cotter slots in the fork and the rod are aligned. First, the gib is inserted into the slot. And then the cotter is driven in. Since the fork ends may open out while carrying the axial load, the gib is provided. This type of joint is used in hose transmission, in steam engines, textile machineries, and automobile parts.
Okay, so those are the things about these three different types of cotter joints. Of course, in addition to these cotter joints, we have one more joint in our syllabus, that is a knuckle joint. So we'll discuss that one later. So first we'll see this cotter joints. So now you might have got some idea what is a socket and spigot cotter joint, then what is sleeve and cotter joint, then jib and cotter joint. So now we'll take one by one and we'll see how we can design these joints for a given axial load. That axial load may be either it may be a tensile load or it may be a compressive load. Okay, right. So now first we'll start with the socket and spigot cotter joint, and we'll try to analyze this joint when it is subjected to axial load. Based on that, you can design the joint. So now this picture will show you all the relevant what you can say drawings or diagrams for our cotter joints. So here, this is what we'll call it as socket. So this is one component, and this is the spigot, the other component, then the cotter. So here you need to design these three components, provided if I take the load is P. If this joint is subjected to an axial load of P, then in order to withstand this load P, what are the dimensions of this P component? So now if I take this spigot, so here it will have this rod is there, and also here I have a collar type of shape is there. What is the dimensions of this collar and what is the diameter of this rod? So you need to calculate those two things. And then if I come to this cutter, what is the width and what is the length and also what is the thickness? So you need to identify three dimensions for this cutter. Similarly, if we come to this here you can see that in case of spy guard also here you have a collar kind of thing is there. So here you have a two diameters. So of course this bottom diameter is equal to diameter of this one, and then the top diameter you need to calculate. What is that value you have to calculate? And similarly, you need to find out. So based on that, not only the diameters. Okay, for the finding out those diameters also you have a different failure criteria. So you need to use all those failure criteria to find the dimensions of the component. So now this figure will show you the front view and top view of this cotter joint. So maybe sectional front view here. So in that you can see what are the various dimensions. So we have shown all the dimensions of the cotter joint here. So in this, of course, you have a side view also here. So from these three views, you can identify what are the dimensions you need to calculate, and also you can estimate all those dimensions. So here, so first thing is D, that is the diameter of the rod. So you have to find out this one. So this side it is D, this side it is D. Of course, here it is not shown. In this view, we have shown here. Then D1 is so the outer diameter, this diameter of the collar. So this is going to be the D1. Then what dimensions you have? D2 is also there. So where is the D2? Okay, of course, here this is D3. So this diameter is outer diameter. This diameter is collar kind of thing is there. The diameter is this one. So for the diameter of this one, we'll take it as D3. Then D4 is this diameter. So D2 you can see it here. Here you can see that this is going to be D2. So here this dimension is going to be D2. So this is D. And anyway, this diameter of this portion of the rod is D. Then in addition to those D1 to D4, you have A is here, B is here, and then T1 is here, and also here you have a, of course, if you know the D, you can take it as D. D by 4 you can easily calculate. So here I have a T, and here I have a L. L is nothing but the length of the cotter, and T is the thickness of the cotter. So B is going to be the width of the cotter at the center line. So B. So you have to determine all those dimensions. So for that, so we need to use various failure criteria. So in what way each component is failed because of this applied tensile force. Of course, the same thing is valid for a compressive force also. Don't think that we designed for only compressive load. The same effect you can see when it is subjected to a compressive load also. So that means the design remains same. Whether it is a tensile load or compressive load, you can use the same procedure for the designing the component. And also here one more important point what we need to remember here is, if you refer the data book, so in the data book he has given the formulas for the design, and then he has given the, what you can say, that is empirical relations. If you open the data book now, just those who have a data book, you can open your data book. So in the data book, you go to this topic, that is cotter joint, which is going to be chapter number 7, which is cotter and knuckle joints in my data book. So it is chapter number 7. I'll go to page number 7.1. So in that he has given what are the various symbols what you are going to use in that. So he has given this picture also. Okay, let me put it in a video mode so that you can also see this. So then I'll come out of the presentation, then only you can see that what I am showing it to you. Okay, so this like this, you have a topic which is chapter number 7 in your data book, which is cotter and knuckle joints. You can see the title, cotter and knuckle joints. Chapter number 7 is there. So here in the first page, he has given all the notations. So that means what you can see it is for cotter joints. So first these are the notations for the cotter joints. Later he has given in the second page. If you refer to the second page, here he has given the notations for the knuckle joint. So that means these are the notations you need to follow for designing of knuckle joint, and then the top and the previous page, whatever notations he has given, these are for the cotter joints. The cotter joint may be it may be either socket and spigot joint, or it may be a sleeve and cotter joint, or it may be a zip and cotter joint. So now you can see that the P, first notation what he has given is applied load or load carried by the rod, which is expressed in newtons. Then he has given D. D is diameter of the rods. D1 outside diameter of the socket. D2 diameter of the spigot or inside diameter of the socket. So D, that is D1, D2, D3 diameter of the spigot collar, D4 outside diameter of the socket collar, B mean width of the cotter in mm. So B is mean width of cotter means, like I already told, the width at the axis of the rods. So that we'll call it as mean width. Then thickness of T is going to be the thickness of the cotter. T1 is thickness of spigot collar. So like that he has given all these things. Similarly, C, thickness of the socket collar. A is distance of spigot end from the slot. L, length of cotter. So then you have sigma T or ST, which is permissible tensile stress. Then SS, permissible shear stress, or sigma tau S, tau, permissible shear stress. Then permissible crushing stress, that is sigma C. So that means these three are the stresses values what he has given. If you go to the next page, you can see that clearly he has given the joint also. You can see the joint also there. So you can and also one more point what you have to remember here is, even in the examination point of view also, they will ask design and draw the cotter joint. So then you can use the data book. So simply you take this, but only thing is you cannot draw like a rough sketch. You have to use pencil and scale, and then you need to draw it neatly for these dimensions. So examination point of view, for this diagram also you have some marks. So therefore you have to do nothing, just you should have a data book. So from the data book you should know what is you have to take, and then how you can use the data book to take the information from the data book, and you can write it in the answer sheet. Okay, so now if I take this anyway, so he has given all the design calculations. He has given for this socket and spigot joint. Here you can see that the first one. So he has given all the design calculations, how to estimate the dimensions of the joint. So you can go through the here next page. Okay, I'll show it like this. So next page, here you can see that. So these are the formulas, all the things you can see here. So you got using these formulas, I can calculate all the given dimensions. So for whatever we discussed, D1, D1, D2, D3, D4. Similarly, A and C, T, T1. So those parameters you can calculate based on all these formulas. So in addition to that, if you look at the bottom here, so he has given usual proportions of socket and spigot joint. You can see it here. Usual proportions of socket and spigot cotter joint. So he has given the proportions. So that means once you know the D value, that is the diameter of the rod, or you can say diameter of the spigot. Once you know that, so from that you can easily calculate the dimensions of other parameters also using some proportional dimensions. So like he has given D1 is 1.75 D. D2 is 1.2 D. So then D3 is 1.5 D and D4 is 2.5 D. Like that he has given the proportions. Similarly, A equal to C equal to 0.75 D, and then B is equal to 1.3 D, then L is equal to 4 D, then T is equal to 0.3 D. So T1 0.45 D, E is 1.2 D. Like that he has given all the proportions. But you have a question now. So why he has given two things? So here to calculate all these dimensions, he has given all these formulas. So but here if you know the D value, if you use these empirical relations, you can easily calculate the dimensions also. But you cannot do like that. So what you have to do is, suppose if you ask in the examination, design a sprocket and spigot cotter joint. So then first what you have to do is, you have to design based on these formulas only. So once you design it, then what you have to do is, so next you need to check whether it is satisfying this equation or these empirical relations or not. If it is satisfies, then it's okay. Otherwise, you need to increase the diameter. Accordingly, these empirical relations. So that is the point what you need to remember. Simply, you have to use this all these formulas to calculate the dimensions of the various dimensions of the joint. Once you calculate that, so then what you have to do is, so that is not yet over. So first what we'll do is, we'll determine the sizes based on these formulas. Let us say first I find out the D1. So let us say I got D1 is of 40 or 50 mm. So now here if I go to this empirical relations, here you have an empirical relation for D1. D1 is 1.75 D. So then before going to D1, I need to calculate D also. So now I have a D and D1. So now I'll check whether your D1 and D are related, something like this. Suppose you got from your calculations, you will got D1 is equal to 0.8 D. So then that is wrong. You cannot choose like that. Always your D1 should be more than D. So therefore, you have to use this relation in that case. If you get a lesser diameter for D1 from this empirical relation, or if you compare with this empirical relation, then you have to use this one. So like that, you need to design the joint. Anyway, we'll see that one by one also. So after that, you can see that the next joint what he has given it is here. This is the sleeve and cotter joint. So for the C1 cotter joint also, he has given all the formulas. You can see that here, he has given all the formulas. So if you click the next page, in the next page, you can see that you have a cotter joint also. This is the, sorry, it's not a cotter joint, it is a knuckle joint. So jib and cotter joint, maybe, I think, I don't know, in the newer version of the data book, they may have given it. But in this older version, this is not. He has not given the jib and cotter joint. He has given the knuckle joint only. So anyway, we'll discuss these things one by one. So, but the only thing what I want to convey to you is, always keep the data book with you and try to see what is the formula given in the data book and what is the formula what we are going to discuss, whether they are matching or not. And also, you should know how to use your data book. Then how to use those empirical relations also. So this is the important. Once you understand this, then it is the only thing is simply taking the formulas from the data book and then you need to substitute the data what he has given in the problem and you need to solve it. So it is quite easy. But only thing is at the same time it is quite confusing also. If you don't know what you have to do, even though everything is available in the data book, you are not in a position to solve the given problem. So therefore, understanding the failure criteria for all the components in different modes is important. Once you understand, then you can easily use your data book to solve all the problems. Okay, right. So now what we'll do is we'll go to the first one, that is socket and spigot joint. So, but every time I cannot come to the video mode and I cannot skip the presentation because so if you have a data book, then you keep the data book open with you and then you can refer the formula whatever we are discussing, whether that formula is available in your data book or not. You can check that also. Okay, so that you will be familiar with this how to use the data book also. Of course, I think the notations are same whatever there in the data book and whatever I put in the presentation, it is same. So you'll get the same parameters in the both the cases. Then I'll go to the presentation mode now. Right. So here, this is the socket and spigot joint or spigot cotter joints. Now we need to identify what are the dimensions. So from the data book, the first parameter or first diameter or first thing what you need to calculate is you need to calculate what is this D value. That is the diameter of the rod. First you have to calculate or diameter of the spigot, whatever you call it is. First we need to compute this value. So that means this diameter first we need to compute. Okay. So for that, okay. So anyway, so here this is the joint. Okay. This is the joint what he has given. It is subjected to a some tensile force here. Then what he did is he draw the free body diagram of these three components. Generally, so in order to identify the failure modes, you have to draw the free body diagram and then what are various forces acting on that one. So that's what he has shown it here. So here it is subjected to P here. Then if you look at here, there is a contact between this socket and spy guard at this location. So this collar will come and touch with this one. So here, so therefore this is the contact surface. Here it will exert some reaction. So there is a reaction between this article called as spy guard and this is the socket. So this is the socket and this is the spy guard. So then to further contact, you need to find what is the reaction. That reaction is met. We'll assume that contact force is uniform. So therefore, for equilibrium, this should be P by 2 and this should be P by 2. So you can see that now this socket is in equilibrium. So this side leftward force is P, rightward force is also total force is P. Then in case of cotter, if you look at the cotter here, so this force is pulling this portion of the cotter in this direction. Then also here you can see that okay, this socket is there. The socket is pulling the cotter here at this location in this direction, even at this location also in this direction. So that is shown. It is same thing here. So reaction always you need to take in opposite direction. So here it is P by 2. Here it is P by 2 this side and P is here. So that is nothing but here this P by 2 is reflected here. This P by 2 is reflected here. This P is reflected here. Then if you see the free body diagram of this spy guard, so it is subjected to a force here, then the reaction should be only at the cotter. So here this portion is inserted into this spy guard here, so here it is going to be the reaction. This reaction you need to consider, that is P here. So this is going to be the free body diagram for, these are the free body diagram for those cotters. So we'll use these free body diagrams to find the dimensions, various dimensions of these three parts. Okay, so like already said, these are going to be the notations what we are going to use in case of these cotter joints, the socket and spy guard cotter joint. So here I think let me okay, maybe I'm not able to open this in this mode. I want to show you the diagram also parallelly.
Sir?
Yes?
Sir, once to the previous slide, sir. Free body diagram.
Free body diagram?
Draw చేసుకుంటాం sir, free body diagram.
Okay.
Sorry, play. అదే ఒక్కసారి అది పెట్టండి సార్, ఫ్రీ బాడీ డయాగ్రామ్ ప్రీవియస్ స్లైడ్.
Want to note it down?
Yes, sir.
Okay, no problem. One minute. Okay. Yeah, note down. If you want, you can note it down. No issue. Is it over?
Completed, sir. Thank you, sir.
Okay, right. Okay, so these are the notations what we are going to follow for this socket and spygard joint. P is load carried by the rods, that may be either tensile load or compressive load. Small d is the diameter of the rods. D1 outside diameter of the socket. D2 diameter of the spygard or inside diameter of the socket. See, this D2 is same for both the spygard as well as socket. For socket it is inside diameter, you can see it here in this diagram. So inside diameter of the socket, this is going to be D2. Here this is also same, this diameter. So this is what we'll call it as D2. So D1 is the D1 is outside diameter of the socket. So outside diameter of the socket is this one. This is going to be your D1. So this is inside diameter. This is D2. This is D1. And D, of course, this is going to be D. Diameter of the rod portion, what we'll call it as D. Even this is also this rod portion, whatever is there, will denote that is D. Then D3 is outside diameter of socket collar. So same thing here. So this is the socket collar. So this total diameter, this diameter we'll call it as D3. Outside diameter of socket collar is D3. Then thickness, T1 is thickness of socket collar. Spygard collar. Spygard collar thickness is, this is spygard. So whatever this thickness is there, this is the collar. This thickness what we'll call it as T1. So that is T1, thickness of spygard collar. D4, diameter of socket collar. So this diameter, okay, sorry, D3 is this one. D3 is, 1 minute, I'll go to that. D3 is outside diameter of spygard collar. So that means spygard is this one. So this is going to be the D3 value. And this is D4 value. This is D4 value. That is outside diameter of socket collar. Then see the thickness of socket collar. So then this one is whatever you can call it as C. This is the thickness of socket collar. We'll take it as C. Then B is the mean width of the cotter. That is the mean width means the average width. If you take top width and bottom width, if you take average, if I take this one as B1 and this is B2, here the width is B2. Then your B1 plus B2 divided by 2. That is what we call it as mean width. We'll denote that one as B. That is going to be exactly the center because this cotter has a uniform width, uniform taper. So the width is average of these two, B1 and B2 at the center. So that we'll take it as B. Then T is the thickness of the cotter. L is the length of the cotter. So thickness, we'll take the here in this view you cannot see the thickness. But this is going to be the length of the cotter. So from here to here, we'll take it as length of the cotter. Then A is the distance from the end of the slot to the end of the rod. So that means if we insert this spygard into this, so there is some distance. Okay, you can see that here in this picture. This one. So this is the hole here. So this is from this point to this point. From the hole to the end of the spygard, we'll take that distance as A. Okay, right? So these are the various dimensions we'll consider or we need to find out for this socket and spygard joint. So for that, we'll use these are the permissible stresses. Sigma T is the permissible tensile stress for rod materials. Permissible shear stress in the cotter is tau, and permissible crushing stress or bearing stress, we'll call crushing or bearing, both are same. Permissible crushing stress as sigma C for cotter material. So with these notations, we'll try to see what are the, how we can arrive the dimensions of this cotter joint. So the dimensions of socket and spygard cotter joint may be obtained by considering various modes of failures. So the first failure is, first, like I already told, we need to find out what is the diameter D. That is D. D is nothing but diameter of the rod end of the socket or spygard. So now for that, what you need to consider is, you can clearly see that from the diagram it is subjected to a tensile load P. So you need to consider the tensile failure. So for tensile failure, area resisting tearing of the rod, that is nothing but the tensile failure is resisted by, this is the area. If D is the diameter of the rod, 5 by 4 D square is going to be the area of the rod. So multiplied by your allowable tensile stress, sigma T will give you the value for the total load carrying capacity of that rod. That is 5 by 4 D square into sigma T is nothing but your P. So we know P value, we know the sigma T value. From that we can estimate the D value. So tearing strength of the rods, this is only the resisting area, and then strength means you need to multiply it by sigma T. We get that is equal to P. So now equating this, P is equal to 5 by 4 D square into sigma T. From that we'll get the diameter of the rod. So we'll estimate the diameter of the rod from this equation. That is the first step in our design. So then what? So that means, so we calculated the diameter of the rod. So that means here this end you have, this end is there, this is D. This we got it now. So next we'll move on to the next dimensions. That is, first we'll consider, so D is same for both the socket as well as spigot. So that is the rod end. Rod end is going to be same for both the things. So that's why first we determine the D value. Then we'll go one by one. So first we'll see failure of spigot. Then we'll go for failure of socket, and then we'll take up cotter failure also. So then failure of spigot in tension across the weakest section. So now this is our spigot. So this is a spigot. So now we have taken this diameter is D2 and this diameter is, we already know, D. So here it is subjected to a P here. So tensile force is P. Now if I pull these two ends with a force of, here the P is acting, here also P is acting. Because of that, there may be a chance of failure across this hole, because here there is a hole, means here the thickness, the material is less, very less here. So it may failure across this one. So now if I take a section here, this is going to be the section. So that means here we inserted or we created this slot to provide a space for the cotter. So because of this hole, rectangular hole in the rod spigot here, so this will make the spigot is weak at this location. So of course we are not considering any stress concentration here, we are ignoring all the stress concentrations. Even though there is a geometric irregularity, we don't bother about that stress concentration. We'll apply some factor of safety and we can eliminate that stress concentration. So we'll talk about only the failures, static failures. We don't bother about the stress concentration factors here. So now because of this, the rod may be, it may break into two pieces, something like this. So now this is the region where it is failing. So now to identify the dimensions of this one, so what I need to do is, that is diameter D2. So we'll use that failure criteria. Here also it is a tensile failure only. So you can see that the rod is breaking into two parts here. This is also because of the tensile load. So now you need to consider the tensile strength of this area. So for this, you have to calculate the area multiplied by sigma T will give you the tensile strength. That should be equal to your applied load. From that you can calculate your D2 value. But here it is not a full circle. If it is full circle, simply I can take area as 5 by 4 D square, D2 square. But in that circular area, you have some rectangular hole is also there. So you need to subtract this rectangular hole. Suppose if it is full circle, then the area is going to be 5 by 4 D2 square. This is the area. So in this, I have a rectangular slot. So what is the area of that rectangular slot? You can clearly see that here. Where is this? So here it is a rectangle with dimensions. Vertical height is D2 and thickness is T. So area is going to be, the rectangular area is going to be D2 into T, but I have to subtract this from this total area. I have to subtract this. So therefore, D2 into T is going to be the area what I need to subtract. So if I multiply this area by sigma T, then I'll get the strength. And if I equate this one into P, from that I'll get the D2 value. But here you can see that I have only one equation. This is only one equation. Here D2 is unknown for me and T is also unknown for me. So I cannot solve this equation with one equation and two unknowns. Then what we'll do is, now we'll use those empirical relations in that case. since the weakest section of spigot is that section which has a slot in the cotter. So therefore, area resisting the tearing of spigot across the slot. So like already said, it is 5 by 4 into dt square is the circular area minus the slot area. Slot area is d2 into t. So tearing strength of the spigot is nothing but you need to multiply that one by sigma t, you will get the tearing strength. So once you got that, equating this load to P, you will get the equation. So but here from this equation, diameter of the spigot or inside diameter may be determined. So he said it may be determined, but here you don't know what is the T value. So without knowing T value, you cannot find that value. So but this is the equation what we are going to use. So for that what we'll do is, we'll use certain relation. So we know that area resisting, okay. So there is a relation between D2 and T. So generally T is taken as D2 by 4. So if you use that relation, you can easily find that. So D2 value. Or else if you use another failure theory, that is not only tensile failure. So here we are considering only the tensile failure. That means the rod is failed, something like this. But you have a crushing also, because you are inserting a cotter here. So there may be a bearing stress here is there. You need to consider that bearing stress also to find or to specify that whether it is this cotter or this spigot is able to withstand that bearing load or not also. So for that, we need to consider the failure of the rod or cotter in crushing. So here again, so the area is only D2 into T. We know the area resisting the crushing. That means, so whatever contact area between the cotter and this spigot. So here the diameter is D2 and thickness of the cotter is T. So it is going to be D2 into T. Then the crushing strength of the rod is D2 into T into sigma C. That is going to be the crushing strength. That should be equal to your P again. So from that, you can find out sigma C is equal to P by D2 into T. So from this equation, what we will do is, so earlier equation, we calculated the D2 value and T value using this equation. Then we'll check that here, whether we'll calculate the sigma C value here, and we'll check that whether that sigma C is within the allowable limit or not. So therefore, from this equation, the individual crushing stress may be checked. So that means, so using the previous equation, let us say I got D2 value is some 40 mm and the T is some 10 mm. I got these two values. So now using these two values, now if I decide I have to take D2 is 40 and T is 10, then with this 40 and 10, whether they are able to withstand the bearing stress or not. So that I am checking it here. So sigma C, I'll use this applied load is given to us. Just I estimated D2 and T, then from that I'll calculate sigma C. This sigma C should be less than your sigma C allowable. Then only your design is correct or safe. Otherwise, you need to modify your D2 value. Accordingly, you need to change the T value also. So that means, first we'll calculate the diameter of the rod, then that is D. Then using the second equation, we'll compute D2 and then T. Then taking the values of D2 and T, we'll check for the crushing strength of cotter as well as failure crushing strength of the spigot, or we can call it as a rod also. So once you satisfied with those values, then we'll move to the next one. That is, we'll move to the socket. So then the failures of socket, again here two failures. First we'll consider the tensile failure. Then once based on the tensile failure, we identify the dimension. Then we'll check for, with those dimensions, we'll check for whether because of these dimensions, the crushing stress is within the allowable limits or not. We'll check that again. So now here failure of socket in tension across the slot. So we know the slot is there for the socket also, not only for the spigot. This slot, a rectangular slot is there inserted in the socket also. That we already seen in the video also I have shown to you. So in order to make the joint, you need to create two rectangular holes. One is in socket, other one is in the spigot. So those two rectangular welds were match with each other. When they inserted into one upon the other, then we'll insert the cotter into that. So therefore, here also socket is there. So then, so because of this socket hole or cotter hole, so then exactly because of the slot, here also it is going to be weaker in this. So then the first kind of failure what you can consider is, so we'll check for whether it is going to fail across this slot. So for that, again, what you have to do is, what is the resisting area you need to consider, and with that resisting area, so if you multiply it by sigma t, allowable tensile stress, that will give you the tensile strength or tearing strength of this rod across this slot. You need to equate that one to the load P. From that, you will get the required dimensions. So once you got the required dimensions, then use those dimensions to check for the crushing strength. Okay, right. So now here, if I take a section here, this is going to be the cross section, or this is the cross section, the section at the weakest across the slot, which one we will consider it as a weaker one. So now here you can see the dimension. This dimension is D1 outer diameter, and inner diameter is D2. If there is no this slot hole is there, that is the rectangular hole is not there in this, then the area is going to be, it is a hollow circular shaft. The area formula is going to be this 5/4 into outer diameter is D1 square, minus inner diameter, that is D2 square. This is the area. So you have a rectangular hole is there in this. So now you have to remove this much portion of the area from that. So you have to subtract the area of this rectangular slot. So then for that I need to calculate what is the area. So that is nothing but, if I take D1 minus D2 is nothing but this distance. So if I take outer diameter minus inner diameter, means I'll get only this one and this one this side, and then this thickness is going to be T. So I have to subtract here is D1 minus D2 into T. So D1 minus, anyway, that is there in the slide. I'll show that to you. Arrange this also. So then this is going to be the area. So 5/4 D1 square minus D2 square. This is the rectangular area. Sorry, this hollow circular cross section area. In that you need to subtract this slot. So this slot is nothing but this slot height is going to be D1 minus D2. Slot width is going to be thickness, that is T. D1 minus D2 into T is going to be the slot area, which we need to subtract from this area. Then if you multiply this one by sigma T, you will get the tearing strength of the socket across this slot. So then you need to equate this one to P. If you equate this one into P, from this we already estimated D1, D2. Sorry, we already estimated D2 value, but in the previous case we estimated D2 value. We have to estimate now D1 value using this relation. So from this equation, outside diameter of the socket D1 may be calculated. So once we calculated the D1, then you need to check for the bearing strength of this socket. So with these values of D1 and D2 and T, you need to check for the crushing strength. So anyway, that he has not given here. You can do that also. So here again the crushing area is nothing but the area, outside area, that is nothing but D1 minus D2 into T. D1 minus D2 into T divided by your P. So that is nothing but P divided by this area will give you sigma C value. So now we need to verify that whether the sigma C is within the allowable limit or not. Right? So this is how you can estimate the dimension D1, that is outer diameter of this socket, outer diameter of the socket. Okay? So outside diameter or outer diameter of the socket. So I think it is already now 10:30. What we'll do is we'll stop now at this point. We'll continue this in the next class. Okay? If you have any doubt in this so far, then you can ask now. So anyway, we have 1 or 2 minutes time. Already 11:30. Okay, if you want, you can ask any doubt. Otherwise, just you respond to the attendance sheet and then you can leave it.